I will now demonstrate the functionality of the wireless tool. In order to start the wireless tool, navigate to the project folder, open the wireless2.m file and click Run. Here you will be greeted with the main window. To the top left, we have this part of the tool that defines the endpoints of the link. This meets the requirement 3B. Here the topographic data is derived using the Google Maps API. This section here defines the path loss models that the program features. This meets the requirements of 3A. You can define the parameters by selecting a path loss model and clicking View Edit Parameters. There's a bug that sometimes causes it not to work on the first run, so you might have to just toggle and then click View Parameters, and here it comes up. And here you see all the parameters we can use to define we can input to the model. So let us get some example parameters. In order to remind yourself what parameters are valid and what is the domain of applicability for the Okumura-Hata model, you can click the help button, and this will basically give you instructions on how to access the help for this particular function. So it says, for example, in order to get information on how to use the Okumura-Hata model, return to the MATLAB workspace, then type help Okumura-Hata. And Okumura-Hata is the name of the function. So let us go to the command window, type CLC to clear everything up, help Okumura-Hata. And here we see, right, all the parameters being well described. So let us return to path loss parameters window and let us put some information in there. 2, 130, 150, 1500, sorry, urban, large. We can also test the model directly by inputting the example usage to the command window. Note that all the parameters are given as a string, even the numbers. And here we see the path loss is 144. And we can do this for all the other models as well. So to save the changes, we click Save and Close window. And that has been saved to our program. So we have fulfilled requirements 3A and 3B. 3C, we have the path profile being generated for the 2 points we defined and the user map defined up here using the Google Maps API. Right. We are also required to calculate the Fresnel clearance as well as the earth curvature along the path for all the major obstacles, and the user should be allowed to adjust antenna heights until the path is sufficiently cleared. Right. Here we see the elevation path here, but the trajectory, and we have determined this. The tool will determine where the major obstacles are, and in this case we have 5 major obstacles, 1, 2, 3, 4, 5, and the X's on top of the obstacles indicate the required total clearance as calculated according to what we did in the show clearance table window. So here we have the front net clearance and the earth curvature. We have allowed 5 meters for tree growth and so on, and the total. So we have met the requirements for section 3D. We also require to determine the free space path loss, time availability, and cell coverage percentage. The free space path loss was will be calculated automatically in the back end when you select your model and put in the parameters, and we have already done so for the Okumura Hata model. And in order to determine the time availability using the Burnett-Vigans model, we can go here, click on link performance, and here this is the table that defines the Burnett-Vigans model, and here we have our parameters, the unavailability, A, B, frequency, and the distance. The distance does not automatically update here, right? So, but what we can do is we can change the unavailability. We can set this to say 2 and see the changes here, the required fade margin, and so on. Okay, let us close this. The percentage coverage has not been implemented. Right, so implement three-dimensional radiation patterns for different antenna types. We could not, as discussed in class, we could not get the parabolic antenna to work. However, we have an assortment of antennas here, the dipole, reflector, and horn antenna. Let us look at the horn. Select the horn antenna for transmit antenna, and here we can see the 3D radiation pattern by selecting 3D and then clicking View TX Antenna. Here we see the 3D radiation pattern loading. We can we can use a data cursor and so on. Software seems to be sticking at the moment. We can close the window here. We can also get a physical plot of the antenna. And we can also look at the azimuth and elevation. The software is taking a little time to load. Now, to get the calculation for directivity, front to back ratio, and other parameters, right click and click on antenna metrics, and here we see we have power bandwidth, the front to back ratio, the SLL. But for this antenna, these parameters are not defined. Front to back ratio is undefined, and so on. Primarily because of the radiation pattern of the antenna. We can also, so we have met the requirements for 6A and 6B, right? The user can also edit the antenna characteristics, view and edit, right? And the user can also change the pitch and yaw. So let's turn the pitch to 90 or 45 and click view antenna. Here we see that the the plot has changed. Let's look at the physical antenna to see. Here we see the pitch has changed for the antenna. Derive the receiver threshold. Alright, so the receiver threshold, right, is calculated in the link performance window, and we get to choose our coding depth, BER objective, our modulation scheme, which can be QAM or PSK or PAM, bandwidth in hertz, noise figure, and we get our receiver sensitivity. The calculations for the receiver sensitivity are detailed in the report. So we have met objective 7. The feeder loss, this 8B has not been implemented, but the link budget 8C has been implemented. If you go here, we can see our link budget is calculated for us. The antenna gains and the path loss is input automatically. We must specify the feeder losses as well as the transmit power, and our receiver sensitivity will be derived from up here, and we get our link margin or system margin calculated for us. And that concludes